In this video, we're going to do some examples of finding the limits of radical functions. Let's say for our first example, we have the limit of x approaches 9 for the square root of x plus 7. We're going to do direct substitution and plug in 9 for every single instance of x. So we have here 9 plus 7, and we get the square root of 16, which is equal to 4. So our answer is 4. So the our square root functions are going to be continuous when our inside is positive. So let's do another example. Let's say we have limit of x approaches 4 for the square root of x minus 2 divided by x minus 4. So let's do some direct substitution. We have the root of 4 minus 2 and 4 minus 4. So that is going to be 2 minus 2 over 0, which is 0 over 0, and it's an indeterminate form. So in order to fix this, we are going to multiply by the conjugate. So we're going to take this, and the conjugate is basically when you multiply by the exact same thing, except you're going to change the negative sign to a plus sign. So you have root of x plus 2, and then root of x plus 2 instead of negative here. So if we do this and do some algebra, we can multiply by that root x and here, and we can also multiply again. We are going to get root of x plus 2, and then here in the bottom we do the same thing. We actually get x minus 4, and in the bottom we have x minus 4 and the root of x plus 2. The reason being because we're going to multiply by that x squared and the root of x and the root of x, so that's going to cancel out. We just get x, and then we multiply that negative 2 times that negative 4. So I just think of it like this. These two and then these two give us this and this. And then for the bottom, I think of it like this. We have x and root of x, so then we get this x minus 4 and root x plus 2. So for the bottom, usually you just keep that. Or in this case, that's what we did. So now we can just cancel out this common factor here. So we get 1 over the root of x plus 2, and we can just do direct substitution at this point. We're going to get 1 over 2 plus 2. Also, you're usually going to want to keep this limit notation whenever you continue before you do direct substitution. So 1 divided by 2 plus 2 is just 1 over 4. And we now have no more indeterminate form. So multiplying by our conjugates is going to remove our radicals and eliminate that 0 over 0. For our next example, let's do limit of x approaches 0 for the square root of x plus 1 minus 1 divided by x. So let's substitute in. We have 1 minus 1 over 0 is equal to 0 over 0. Indeterminate. So we're going to take this and we're going to multiply by the conjugate. We have multiplication by root of x plus 1, and we have root of x plus 1 down here as well. We have 1 here and 1 here, except we're just going to change this to a positive sign from that negative sign. Now, if we multiply, we get x plus 1 minus 1 here, and in the denominator, we get x. We're just going to keep it x and root x plus 1 plus 1. So here we can see we had this square times the root times a root, right? So that canceled out the root. And then we just had this negative 1 times that 1. So then that became negative 1. Now what we can do next is we have x plus 1 minus 1. So this cancels out. We just have x in the numerator, and you still have your denominator. X plus 1 plus 1. Now you can cancel out that x. We're just left with 1 over root of x plus 1 plus 1. Now you can do direct substitution. You have 1 over 1 plus 1 is equal to 1 over 2 for your limit. And again, you want to keep the limit notation, but while doing it, it's a little weird to remember to write again. It gets a little bit tiring, but that's a good habit to remember to write it at each step. So now for our next example, let's do the limit of the root of 9x squared plus 1, all divided by 1. as it approaches infinity. So we're going to factor inside of the radical. We get x squared, 9 plus 1 over x squared, all divided by x. So this x squared under the root, you have to think of it as an absolute value because we are looking at x approaching infinity, right? So here we have the absolute value of x, and then we have 9 plus 1 over x squared that's left inside the radical, all divided by x. So again, because we're going towards infinity, if you have the graph of your x squared, you can see that on the right side where we're approaching positive infinity, we are going up to positive infinity. So what's important is we have to look at this because when we have that square root, it's going to give us a positive and negative solution. However, we only want to look at the positive solution of the behavior of x squared because we're looking at the behavior as it goes towards infinity, not towards negative infinity. So here, our next course of action is we have root 9 plus 1 over x squared. So then what we have is, as x approaches infinity, 1 over x squared, this right here, is going to go towards 0, and we still have a root of 9. So the root of 9 is going to be equal to 3. And again, that's because our root of x is just going to be equal to x as x approaches infinity. So then that's why we had that x here and this x here, and then that x canceled out, which is why we were left with an answer of 3. So we had to factor out the denominant power inside of the radical, and then from there, we just used our knowledge of our function that we were approaching the positive side in absolute value, and we know that we lost that left side. Then we just canceled out that x, and then we looked at 1 over x squared because that was the only term inside of our function that we were evaluating that had an x inside of it, which was going to change as x approached infinity. We saw the behavior of that is just going to keep getting smaller and smaller as we divide by increasing values of x. 1 is going to approach 0. So then we just took the square root of 9 and we got 3. So for our next example, let's do the limit as x approaches negative infinity. You're going to have 16x squared plus 5 divided by x. So the first thing you want to do is you want to factor. Let's write this here. Gonna factor this. We get the root of x squared, 16 plus 5 over x squared. Now this is all divided by x. Next, you can write this as limit x approaches negative infinity. We have x absolute value, and then we have 16 plus 5 over x squared. Now we have division by x there. So because we know we are going x approaches negative infinity, that's going to make the absolute value of x equal to negative x because we're looking at the left side this time. Now, if we plug that back into our equation, we have negative x instead. So limit as x approaches negative infinity for negative x times 16 plus 5 over x squared is all divided by x. So then after this, you can just cancel out that x in the numerator and denominator. You get limit as x approaches negative infinity for these negative 16 plus 5 over x squared. So now we just look at as x approaches negative infinity, right? So this part right here, this is going to approach 0 as you keep dividing by a larger number. Now, all that's going to be significant is we just have that negative on the outside, and the square root of 16 is going to be 4. So your answer is just negative 4. So the reason why this works is because we had that square root of x squared is equal to the absolute value of x, not just x. Now let's do our next example. Let's say we have limit as x approaches to infinity, and you have root of x squared plus 4x minus x. So we are going to have infinity minus infinity form if we were to do direct substitution here, right? Because you have an infinity right there. That would be infinity minus infinity, and then this is going to be indeterminate. We can't evaluate that. So what we're going to do instead is we want to get rid of the radical by rationalizing. So let's take this, move this over here. We're going to multiply the top and the bottom by x squared plus 4x, and we're swapping the sign right here. We have positive x this time, and do the same thing for the denominator as well. So what we end up getting is x squared plus 4x minus x squared. And then we had divided by the root of x squared plus 4x plus x. Now, after this, we can take 4x in the top. And then we have root of x squared plus 4x plus x. Because that x squared canceled out. Next, we can factor out this x squared here. So if we do that, we can take that x out. We take the square root of x. It's just going to be x. And then we still have 4x up here. We have 1 plus 4 over x. We had an x here and we had an x here. So then this is going to be plus x. Actually, that x was on the outside, so that's just plus x. Now you can cancel out the x that you have here. That's multiplication, so you can cancel this one, but that's addition, so you cannot cancel this one. This is a plus x outside of the radical. Now, after this, we're going to look as x approaches to infinity, right? So as it approaches to infinity, right now we have just 4 over 1 plus 4 over x plus 1. So we can see that this is going to approach to 0 as you keep dividing by a larger and larger number. So if you evaluate at this point, you have 4 square root of 1 plus 1 is just 4 over 1 plus 1, which is just equal to 2. So 2 is your answer. Now, for our next question, let's do the limit as x approaches to 1. So you have x minus 1 divided by the square root of x plus 3 minus 2. Now, you're just going to substitute in, and if you substitute in, you get 1 minus 1 over square root of 1 plus 3 minus 2, which is 0 over square root of 2, the square root of 4 minus 2, which is 0 over 0. Now, what we do instead is we rationalize the denominator as we've been doing. So we're going to multiply by the square root of x plus 3, and then we have square root of x plus 3, and we have 2 here. We're just going to change this to addition. So this time we're looking at rationalizing wherever the radical is, right? So it doesn't matter whether the radical was in the numerator or denominator. We're still going to multiply the entire fraction by this because this is all equal to 1, correct? So it's just the same thing as multiplying by 1 because numerator and denominator are equal, and we can get rid of the radical that way. So our next step is now up here we just have x minus 1. We're just going to keep it root x plus 3 plus 2. And then in the denominator, let's see here, we have this multiplied by this. That's going to cancel out the root. And after that, we just have negative 2 times positive 2, which is going to give us negative 4. So we get x plus 3 minus 4. Now, what can we do next? Well, this is going to simplify to x minus 1. And this is x minus 1 times root x plus 3 plus 2. So then you can cancel out that x minus 1 right here. And you have, this is equal to the square root of x plus 3 plus 2, which is, now we can substitute in our 1. That's going to be square root of 1 plus 3 plus 2, which is 2 plus 2, aka 4. So now let's do another example. Let's say we have question 8. Limit as x approaches to positive infinity. We're going to have 25x to the power 4 plus x divided by 5x squared minus 1. You're going to factor inside of the radical. So you're going to get x to the power 4 times 25 plus 1 over x to the power of 3. So that's because we had that x before. Here we can do that as well. So remember, when you have when you have the quotient of two exponents, you have x over 4 divided by x over 3, for example. That's the same thing as x over 4 minus 3, which is the same thing as x power 1, aka just x. So now let's think. What can we do next? So this is over 5x squared minus 1. Well, we know that we can take this out because this has an even power and we have a square root there. So this can be x squared, absolute value. And we have 25 plus 1 over x to the power of 3 still inside. All divided by 5x squared minus 1. So because we know that x squared is going to be greater than or equal to 0, that means that we have absolute value of x squared is going to be equal to x squared, again, because we're approaching positive infinity. And we're looking at this side here as we go to positive infinity values of x. Next, what we can do is we'll take that. We have x squared, and we have 25 plus 1 over x to the power of 3 divided by 5x squared minus 1. So we're going to divide the top and the bottom by x squared. Let's take this and divide that by x squared. Take this and divide that by x squared. So we get, in the numerator, 25 plus 1 over x to the power of 3, because that's going to cancel out that x squared. And in the denominator, we're going to get 5x squared over x squared. And then we have negative 1 over x squared. So just to redo that, we have 25 plus 1 over x cubed. And you can cancel out that x squared. So you have 5 minus 1 over x squared. So if you look at x approaches positive infinity as we're thinking, right, we can see that this is going to approach 0. This is going to approach 0. So then you're basically left with the root of 25 over just 5. So that's just going to be 5 over 5, which is equal to 1, which is your answer. Now let's do another example. Let's say we have the limit as x approaches to 0 for 1 minus 2x minus 1 minus x, all divided by x. So if you substitute in, you're just going to get 0 minus 2x minus 0 minus x all over 0. That's going to be an indeterminate form. So we just are doing the conjugate strategy again. So we can multiply the top and the bottom by this. That's addition. So we are going to have 1 plus 2x minus 1 minus x all over x, 1 square root of 1 plus 2x plus square root of 1 minus x. So this is going to simplify. Up here we have a 1 and a 1 there, but that's going to cancel out that negative 1. And then we have a 2 and then a minus x there. But that's going to be multiplied by that, so that's actually going to become positive. So in the numerator, we have 3x, and then in the denominator, we still have this entire thing here. Next, we can cancel out some things. We can cancel out the x. We get 3 over 1 minus 2x plus root of 1 minus x. We get, now we see that as this goes to infinity, or I mean as x approaches 0, as we get smaller and smaller values, you're eventually going to have that this is going to go to 0. And then this is also going to go to 0 as you keep plugging in values that are closer to 0. So then you're ending up with just 3 over the root of 1 plus the root of 1, aka 3, 1 plus 1, aka 3 over 2. Now for our last question. Let's say that we have the limit as x approaches to negative infinity. You have the root of x squared minus 6x plus x. Now we're going to factor inside of the radical. We get the root of x squared, 1 minus 6 over x, plus x. Now, after this, we can see that this root of x squared, this is equal to the absolute value of x. So that's just going to be absolute value of x there. Rewriting this whole thing, we get 1 minus 6 over x plus x. Now, what we know is that since we are going to approach negative infinity, we are going to have the absolute value of x is equal to negative x. So we can substitute that in again. Now, next, we know we can factor out x, actually. So if we factor out x from everything here, we have an x here, and we have an x here. So that's just going to be x on the outside of the outside thing, right? So we have 1 minus the root of 1 minus 6 over x. Now, we have this radical. We don't want the radical. we're going to multiply by the conjugate. So we have, in the numerator, we have 1 plus the square root of 1 minus 6 over x. And in the denominator, we have 1 plus the square root of, or 1 plus the square root of 1 minus 6 over x. So we're going to end up with x 1 minus 1 6 over x. And then here we have 1 plus the root of 1 minus 6 over x. So this, in the numerator, we can just cancel out that 1 minus 1. We just get 6 over x up here. We still have this x out here. And then in the denominator, we still have the same thing, 1 minus 6 over x. Next, we can cancel out one of the x's. So in the numerator, we have 2 x's right now, right? So then that can cancel out. We just get 6 over 1 plus the root of 1 minus 6 over x. Now, we are looking as x approaches to negative infinity, right? So then as we go to negative infinity, this is going to be dividing by larger or more negative numbers. So that's going to approach 0, right? And then this is going to leave us with 6 over 1 plus the square root of 1, aka 6, 1 plus 1, aka 3. So now you know how to evaluate radical functions and take the limits of them.